we don't say. And has been here ever since. So, Joe?
Well, I've not quite been here ever since. I was with you for 3 years. And I was
Yes, that's correct. Speaking of which, how's the tennis?
See if this works.
Oh, you're using a laptop? Push the button.
Laptop button?
Yeah, push the button.
Okay. It is plugged in.
It's hard to describe.
Maybe it's got a filter.
No, it's just
Oh, I see.
Trademark? Hard disk, like in your computer.
Which camera are you using?
I don't know. It's not mine.
Oh, it's a JVC, I see. JVC. Now I understand how this is. I thought it's a straight name for a camera. I get the
I haven't looked at the result on the computer, so I can't tell, but I think it's average. The problem is the sound usually.
Yeah.
Without a proper microphone.
Oh, now it's Okay, let's have a word.
Okay, right. So it's a good idea to insist to use your laptop. I think there was a filter preventing some pictures from appearing past the security.
Yeah, there were 5 there.
So, right. I wish I could say that I knew Prakash, when he looked like that, but I don't think anybody would believe me. I mean, look at the amount of hair, then and now, and there's not gonna. It just doesn't quite work. But I thought I would say I'm glad actually Stephen used this picture. I started panicking during his talk. I think he has better decency than me. And I thought I would say something about Prakash. And then I was lots of stories about Prakash. But then I thought, if you live in a glass house, as I do, ancient throw stones. So I'm going to tell you a story about Prakash once visited Oxford. This was before my time, and he looked something like that. And then he was meeting with this gentleman at some point. Did anybody recognize him? That's Tony Hoare. Who looked like this when Prakash looked like that. And Tony called Prakash to speak with him and so on and apologize that he wasn't going to be able to come to the seminar. And he explained that in fact he had this long-standing engagement to attend a seminar, another seminar of this gentleman, Roger Penrose. This was an invitation-only seminar. It was a very kind of fancy affair. And which was scheduled at the same time as Prakash talk. I said, oh, that's a shame, I wish I could have gone to that seminar because, I'm really a physicist, underneath. And in fact, I used to work on things that, Penrose are interested in, so that Stephen Hawking are interested in. And Prakash started talking about his work and said, well, I did this and Stephen Hawking did that, and then I did this, and then, and then he proved that. And, back in the day, and so Tony kind of politely was listening to Prakash, and somebody said, pulled ahead of you, didn't he? So, I don't know if it's true, but we'll pretend it is. Okay. So, I'll come now to the PowerPoint presentation. As you can see, I've got only 2 slides. So, I'm going to do slideshow. Right. Great. So the Polyhedron-Hitting problem. This is, I'll talk to you. It's going to be Barbados style board talk in the Prakash style, but I will talk to you about this polyhedron-hitting problem. This is joint work with James Worrell, who most of you know as Ben, and my PhD students, Nancy Jonah and Joan Sousa Pinto, who I think are in the room. Both of them, yes, they are. So the problem is succinctly stated. So you work in a finite dimensional vector space. So let's say you're working in Q to the m, and you've got some matrix A, square matrix, a linear transformation in that vector space, and you have a starting point in the vector space, okay, and you have a target V, which we can take to be many things. We can take it to be a point, we can take it to be a vector space, we can take it to be a polyhedron, as you know, in this case, a semi-algebraic set. There are all kinds of variations on this problem. But the basic data is you've got this linear transformation, this starting point, and this target. And you look at the orbit of this point under repeated application of this linear transformation. So let's say x starts here, and then maybe, you know, that's ax. And here is, you know, a squared x, and so on and so forth. So these points kind of go around, and they thus, you know, define the orbit of x under this linear transformation. And here is maybe your target polyhedron. So that's V. And the question is, does the orbit ever enter the polyhedron? So do you ever hit the polyhedron, right? And so that's the basic kind of setup, the basic problem that I want to talk to you about in this talk. And there are lots of generalizations and lots of specializations and so on. It's actually quite a large field. It's about, I mean, these things are discrete linear dynamical systems. And they appear everywhere. So they appear in biology, they appear in economics, they appear in stochastic modeling. So for instance, if you take A to be a stochastic matrix, so Markov chain, then this is an x as stochastic vector. Then this is the orbit of the sequence of distribution you get from moving into this Markov chain. And then you can ask questions about this orbit. These become model checking problems on Markov chains. Or if you have a program such as while, and here you have some linear condition L, do x is assigned ax. You can even add plus a vector b if you want. You can make it affine, and you can fold the affine into, expand the dimension by 1 and fold it into, make it linear again. And you can ask about the termination of such a loop, right? So termination of such a loop is it ever the case that this linear condition is satisfied? And that can be written as hitting some polyhedron, or, you know, it's a conjunction of, the polyhedron is just a conjunction of inequalities and so on. So it occurs also in quantum computing. If A is a unitary matrix, then basically this will describe the effect of transformation in a quantum automaton. Usually you have several of these unitary matrices at play. And usually it's not so much hitting a polyhedron, but you've got this projection operator. But you know, people have used very, very similar techniques in quantum computing. And where else does it occur? Yeah?
Are you assuming V is compact? Or would it be like...
No, I'm not assuming V is compact, but there are lots of variants, like I said. You could assume, yeah, you could look at the restricted case in which V is compact, or indeed, and I think my PhD student said, oh, if it's compact, it's polytope. If it's bounded, there's polyhedron. So I don't know if that's completely true, because there are other Wikipedia entries that say exactly the opposite. So, there's a duality there between polyhedron and polytope. Am I forgetting other applications? Sorry? Oh yeah. So that's biology. Anyway, so these things come up all over the place. But that's the propaganda. So I'll tell you a little bit more now about the history. So there are various. This problem also has various branches that kind of converge and diverge and so on. So this is not the sort of most ancient history, but there's this problem. So Harrison wrote a book in 1969 called Linear Sequential Machines, and in it he defined the problem of, one of the things he did, define the problem of accessibility in linear sequential machines. And what it boils down to is not immediately equivalent, but actually, after a little bit of linear algebra, it boils down to the situation in which you're asking this polyhedron-hitting problem with actually a target V which consists just of a singleton point, let's say y. Okay, so you're just trying to hit one point. And he didn't know whether this was decidable or not. In fact, it's not obvious it's decidable, right? You've got this thing that's going around, and I mean, if you hit it, of course you find it, but if you don't hit it, how do you prove you never hit it? And then so a number of years passed until Schenck, who was a mathematician, published in 1979 in Discrete Mathematics, a math journal, solved it, showed it was decidable for the case of m equals 2. So again, it was just a single point as target. So just a 2 by 2 matrix. And already that was non-trivial because that got published in a reputable journal. And finally, there was this famous paper by Cannon and Lipton, which I think some of you have probably heard about, so called the orbit problem. So that was in stock 1980. And then they had the JCM version in 1986, I think. And basically what they showed is that the orbit problem is solvable in any dimension, so not just m equals 2, but in fact arbitrary dimension for a single, but just for a single point, a zero-dimensional target, just a single point, in polynomial time. So that was a big sort of big advance. So completely solved the Harrison problem, and had this polynomial time complexity. And then in the conclusion section of the journal paper, they speculated that other instances might be solvable where you look at slightly more sophisticated targets. So in particular, instead of looking at a target which consists of a single point, they said, well, what if the target is a linear subspace? So the simplest one you could have would just be a one-dimensional linear subspace. Or indeed, what if the target is a plane, a two-dimensional subspace, through the origin, or you can look at affine versions of these things. And they speculated that in low dimensions, this would probably, they'd hope it'd be decidable. They weren't sure about polynomial time. But they said in higher dimensions, it's going to be hard. And the reason that they thought it was going to be hard is because you can express some difficult problems if you allow yourself to have targets, so vector space targets of higher dimension. So there's this thing called the Skolem problem. So the Skolem problem talks about linear recurrent sequences, but they're very closely related to these things. And so in the Skolem problem, when we phrase it in this terminology, you have a vector u. Okay, so let's say vector u in, we can just work over the integers, but the rationals would be the same thing. But let me just work over the integers. So u and zm, u and v are vectors in zm, and you've got this linear transformation. Let's say now they've got integer entries, but like I said, all this applies over the rationals. And you're asking whether there exists an n such that u transpose a to the n v is equal to 0. So equivalently, a to the n v is in u perp. Is it like this, u perp, I guess? So anyway, by this I mean the set of w such that u dot w is equal to 0. So that's a hyperplane of dimension n minus 1 if you're working in dimension n. And yeah, like I said, maybe I should have just done this over it's hard over the integers is what I meant to say, but if you want to talk about vector spaces, let's just imagine we're talking about the rationals. So this becomes your target V. This is your starting point X, and this is your linear transformation A, right? So this is an instance of the orbit problem in which you've got a high-dimensional target as a vector space. Well, the decidability of this problem has been open for 80 years. It's a very difficult problem, and Terence Tao has written about it, and Richard Lipton's written about it, saying it's an embarrassment that we don't know how to solve this. I think Terence Tao says it's outrageous that we can't solve this problem, but we can. The only thing that is known is that it's known to be decidable for m less than or equal to 4. Okay, so for 4-dimensional matrices, but not any higher. Even 5-dimensional matrices, it was announced to be decidable some time ago, but the proof was wrong, and I think it's more or less been retracted now. So even this result is non-trivial. This result uses some high-powered analytic number theory, such as Baker's theorem, which earned Baker the Fields Medal in 1970. And so this is, and there are no known proofs at order 3 and 4 that don't use things like Baker's theorem, in addition to using all kinds of things like p-adic analysis and a lot of other techniques from algebraic and analytic number theory. So, coming back to Cannon and Lipton, they said, well, look, we think that for low-dimensional spaces as targets, it should be possible. Obviously, for high-dimensional spaces as targets, it's going to be very hard because it implies Golem, and there's something. But they didn't prove anything. This was left open until 2013, when so that's Chonev, myself, and Ben. So that's PhD student and my colleague Ben Worrell. So that was in 2013 in Stock, where the result we showed was that if V has dimension 1, so if V is a line, then the orbit problem is decidable in polynomial time. Okay, so just like 0-dimensional. And if V has dimension 2 or 3, it's also decidable, but non-polynomial time. The best we could do was to decide it in NP to the RP. So anyway, this is within D space, but we don't know how to do it in polynomial time. And for dimension 4, we don't know how to do it, because we should show that for dimension 4, if you could solve it for dimension 4, then you could solve the Skolem problem for dimension 5, and that has been this long-standing open problem. So already for dimension 5, it's quite difficult. So okay, so then, but this is for vector spaces as targets. Coming back to this polyhedron, so here, if you recall, you've got a vector space, and now you have a target, which is, let's say it's this polyhedron, this two-dimensional polyhedron. So what's a polyhedron? Well, it's an intersection of half spaces. Okay, so you've got this half space intersected with this half space intersected, and so on. So this gives rise to more complex instances of, you're not trying to hit a vector space, you're trying to hit half of the vector space simultaneously with another half and simultaneously and so on. And these things are affine in general. They're not going to be linear, which complicates things. So we were able to solve this finally. And rather than draw the table, here's what we found. So this is the K is the dimension of the target. So the polyhedron has an intrinsic dimension, which is the dimension of the highest dimensional small bulb that you can fit inside the polyhedron. And M is the ambient space, if you recall. So for targets of zero-dimensional targets, these are basically just points, or just collections of finite collections of points. This is doable in polynomial time. Well, that's Cannon-Lipton's result. For targets of dimension 1, already we don't know how to do it in anything better than p-space, or actually a little bit better than p-space in the sense that it's somewhere in the counting hierarchy or something like this, but we certainly don't know how to do it in polynomial time. For targets of dimension 2, likewise, we can do it in p-space. And for targets of dimension 3, we can solve it provided that all this takes place in a three-dimensional space. So if you're in if you're working in three-dimensional space and you've got a full dimensional target, then you can actually solve it. So this is what this says. However, if the dimension of the ambient space is 4 or more in the case of a three-dimensional target, then this red thing here, it says SK5, then this problem is hard for Skolem of order 5. Okay, so the Skolem problem at order 5, which is known to be open, if you could solve for any value of m and k such that m is greater or equal to k plus 1, so m is greater or equal to 4 and k is equal to 3, then you could solve, if you had an oracle to solve that, you would have an oracle to solve the Skolem problem at order 5. So this is kind of a hardness result if you want. Now what happens, so for instance here at 4, 4, there's there's a D here. So this is another kind of hardness result. This is a hardness result for some hard Diophantine approximation problems in number theory. So again, it's not an undecidability result, but all it says that if you had an oracle to solve this problem in ambient space dimension 4, target dimension 4, then you could solve these hard Diophantine approximation problem that analytic number theorists tell us, oh, we don't know, we don't even know how to begin to attack these these things. Okay, so this is the landscape, and then here you've got hardness for both Diophantine and for Skolem and so on. So this kind of gives you a picture of the decidability, certainly landscape of the Polyhedron-Hitting problem. Now this is so this looks like, oh, it's not, it's a nice picture, it kind of completes. In fact, there are lots and lots of open questions still. I mean, this is just one. This is one particular problem one can look at. I mean, you're looking at these polyhedra. There are all kinds of. First of all, you can put restrictions that all of a sudden make these hard problems go away. So Ben's going to talk about that in the next talk. Some of these things, but there are also all kinds of different problems you can ask. So the message I'm trying to send is that we've just barely scratched the surface. I mean, this is something where we've been exploring these problems, which for whatever reason have not been studied before, have only been studied before in very limited instances. And we feel we're just at the beginning. There are lots and lots of open questions and things to do. So I think I'll stop here.
Supposing you had not one matrix but two or more,
things become decidable very quickly. Yeah. So if they're I mean they're very so very inverse problems like this, like mortality, which are known to be undecidable, even at
223 by 23 matrices.
yeah, 23 is the in case of 2 by 2 matrices, I think I'll show it was decidable, but in case they're unitary, in fact, and you've got a semi-group of matrices, the unitary matrices, then these things, such as threshold problems, which are equivalent to hitting a half space, these things become decidable. And so this is work of people like Hoyren and Blondel and these people. So when they're unitary matrices, these correspond precisely to quantum automata. Then all of a sudden, this is why I mean that
even with multiple
matrices. So which is why I'm saying that there's a huge, highly dimensional landscape of problems to explore there. Because as soon as you change something, all of a sudden you have not only interesting open questions, but also interesting problems that have high relevance to some area of computer science or this, that, or the other.
Just a note, when you have two matrices and they commute, it's actually, you don't
Oh,
have
yeah. So this is,
it's called the ABC
the ABC, well, they regret that thing.
Well, yeah, sure.
Yeah.
Not that ABC
So if two matrices and they commute, then what happens?
Yeah, then like the decidability results don't hold and you can actually.
Yes, that's right.
Whatever, Steve.
If I interpret this table correctly, you're not saying that the Diophantine problem and SK5 are equally hard as each other, but you're saying if there's a solution to this problem,
Yes.
the certain values of K and M, then D and SK5 will be.
That's right, that's right. So if SK5 is solved tomorrow, that doesn't quite solve this thing yet, I don't think. I mean, we'd have to look, but yeah. So I think the implication, it's one way. So it's a hardness for this square, for this entry in that.
But if you can solve your problem for M and K in the right range,
Yes.
will you also be able to deduce that D and SK5
Yes.
are equivalent? Because
Oh, no, sorry. You won't be able to deduce the D and SK5. D is a completely different flavor from SK5.
Okay.
I wouldn't, I mean, didn't have time, but this is about estimating the Lagrange constants of these logs of algebraic numbers and these things where, even for pi, people have no idea what it is. So.
Could you say a bit about how the algorithm works?
Yeah, very, very briefly. So the algorithm, basically, you're going to be looking at, you're going to put this matrix in Jordan form, and you're going to be looking at how the eigenvalues.
I mean, the algorithm itself is completely trivial.
You just get numbers for n.
Yeah. Yeah, sure. No, but I mean, well, yeah, that's not particularly helpful.
It's worth saying that the algorithm is bound n, and then.
Okay, nobody gets lunch until you come, those people who have the algorithm.
No, I mean, this is I mean, you place a bound on n. Indeed, the algorithm tells you, ultimately, if there's such a solution, there's a bounded solution on n, and then you can explore. But the point is, you get these bounds by looking at, you use spectral theory, and then you use these techniques from analytic number theory to analyze the behavior of these eigenvalues as a function of n. How they move on this course, and so on. But I can't say much more than that.
And so when you miss the target, do you go to infinity or do you stay around?
No,
There's
no,
nothing?
you can miss the target and stay bounded, yeah. So over the rationals, imagine a Markov chain. And you say, do I ever hit, I've got this Markov chain and I've got this initial distribution, which is, it's going to be here. Let's say you're in the initial state initially. And then you ask, do I ever end in the state a half, 0, 0, 0, right? Well, this is going to be, you're going to be dense, right? It's a Markov chain. All the vectors are going to be stochastic, but it could be that you never hit that particular vector. So this is, so diverging to infinity is one way to place a bound on n, but sometimes it's more, so you need to use, p-adic norms to, that not Euclidean norms, and so this is where the algebraic number theory if that's.
So if you add a little noise to your linear transformation, then it becomes a lot easier?
Yeah. And there are papers on that, which is why, again, this is like, yes, you can start looking at epsilon approximation